So I'd just like to sort of welcome everybody, and in particular, some of our guests. I know Peter has reached out to some colleagues and previous speakers who are also have a sort of a connection, if you like, with particularly the history of astronomy and those sorts of related topics. So you're very welcome, and of course, welcome to all our club members as well. So tonight we're very privileged to welcome our speaker, Dr. Rebekah Higgitt. And Rebekah has recently taken up the post of Principal Curator for Science at National Museums Scotland. I'm not quite sure where physically you're based, Rebekah, at the moment, but it doesn't really matter, I suppose. Previously, she was senior lecturer in the School of History at the University of Kent, and we have had one or two other speakers from the University of Kent as well, so in great company. And before that was the curator of History of Science at the National Maritime Museum and the Royal Observatory, Greenwich. So we have a connection there with one or two other people, including myself, on this meeting. And currently completing a project on the cultures of knowledge and practice in London. And from next year, we'll be working on digital humanities project on the scientific instrument makers, which is pretty much very well connected with what she's going to be talking about this evening. Rebekah's talk is going to be all about, or focus at least, on British expeditions organised to observe 18th century transits of Venus. Very rare phenomenon, and as I'm sure she'll explain. And so I'm not going to steal any more of Rebekah's thunder, because I'm sure you can tell us a little bit more of introductory remarks about yourself and the talk, but I will hand proceedings over to Rebekah.
Thank you very much. Hello from Edinburgh. I am actually in Edinburgh.
You are, okay.
I managed to move in the summer when we were able to do such things, which was nice to have one lockdown in one location and another in another. So yes, I've got less bored of some of the local walks than some people, I suspect. Can you see my PowerPoint?
It's just starting to share. It's just okay. Gonna, I'll tell you when it's arrived. It's warming up.
Yes.
I've got a blank screen at the moment, but it is saying it's viewing your application. So, and I can see your cursor.
Okay.
Don't know if you want to move the cursor. Oh, there we go. There we go. We have the title page.
Okay, brilliant. Yes, this is a new system. I've got very used to Zoom, as we all have, and somewhat used to Teams, but WebEx is a new experience for me and my computer that I think is rather slowly getting used to it. So I'll do my best. This is a topic that I think will be quite familiar to some people, the people with connections to Greenwich. Louise and Lee, I know, working on the history of the Royal Observatory as well, Louise's area, of course. So some of this will perhaps be familiar, but there'll be more to discuss, I hope, as a result. So I'm starting with an image here from the National Maritime Museum, and quite a lot of the images here are from there, from the time that I was working there, and of course that coincided with one of the last transits of Venus that we had, the last one that happened certainly in my lifetime. And this is, though, not to do with the transit of Venus, and I'll try and explain how we get from one to the other. So this image is from the 1780s, from the third circumnavigation of James Cook, and it shows the ship's Resolution and Discovery in the Society Islands. You can see just about, I hope, their camp on land. And there are tents there, including probably tents that are observing tents, so marking the location of instruments and workspace of some expeditionary astronomers, as I like to call them, those astronomers, observers who've been brought on the expedition overseas. And that location of tents and particular kinds of instruments inside them is really what I mean by precision exploration from my title. So, as I say, not a transit of Venus, but I'll sort of focus on the links. And I'm also doing a British story here, which is not to say that similar things couldn't be told about other countries, particularly France in the 18th century. But it's the case I'm familiar with, and I think it's an interesting one. And it very clearly shows how there was an opportunity to embed particularly precision scientific work onto naval voyages, and how that was created and then further exploited and developed. So this image is a long way, of course, from this, which might be a more familiar one. And nothing's happening when I try and advance my slide. Okay, there we go. A more familiar one for people who've looked at the history of the transits of Venus, a reimagining of the first time that we know of that a transit of Venus was ever observed in 1639 by Jeremiah Horrocks. And of course, this is a late 19th century picture imagining what it might have been like back then in the 17th century.
So
yes,
it's just caught up, Rebecca. Sorry, it was still on the title slide. It's just caught up on my screen.
Okay, I'll try and remember that things might be going rather slower, and you might not be seeing what I can see. But let me know if there's a problem. We can work it again and perhaps swap slides. So yes, this is, as I say, so it was one of the first occasions that the transit of Venus was actually observed, and not long after they were first predicted as a rare astronomical event, as I'm sure you know. And Johannes Kepler made a prediction, although died before he would have a chance to observe them. First one in 1631 and 1639. At this time, of course, the transits of Venus were of interest to a particularly small, really, group of astronomers interested in testing the accuracy of predictions that were made by astronomers from existing astronomical tables. And also at this period, a way of testing the relative accuracy of different models. So particularly the heliocentric elliptical orbit model of the solar system that Kepler had put forward. Also an opportunity to get some sort of a sense of the actual scale of the universe, rather than a sense of the relative sizes that could be fed into that model that Kepler had made. And that's something that Jeremiah Horrocks, who's imagined in this painting, did, seeing that when you see the small disk black dot of Venus passing slowly across the bright disk of the sun, that it was rather further away than they perhaps thought it might be. It was a very small dot against the sun. So how do we get from this darkened room, projection of the sun, to that image of ships and exploration? I'm not going to say a great deal about what transits of Venus are, because I suspect with this audience that you probably already know that it is an alignment of the Venus and Sun and the Earth that occurs in rare occasions in pairs that are then well over a century apart. And that if you want to see the whole phenomenon of Venus moving across the face of the Sun, you probably would need to travel to do that. So it was the need to travel to collect that kind of information, to make that kind of observation, and also a climate in which the potential usefulness of doing things like that was beginning to be much more widely supported. That takes us on to the next stage, that moves us away from that early 17th century occasion, and that very much defined the career of Edmund Halley, who was made a captain in the Royal Navy. Hopefully you will be able to see my slide that I've moved on to. And we can think about ourselves in the later 17th century and early 18th century, in a period where there was much more collective support for scientific investigation and technical experimentation from, for example, things like the Royal Society, founded in 1660, and also increasing interest and support from monarchs and parts of government, particularly more military aspects of government. So the Admiralty, the Navy, the Ordnance were interested in accessing developments in science that would support their interests. So, for example, we see the foundation of the Royal Observatory in the 1670s, funded by the Ordnance and founded at the behest of the King. And that's an institution into which Halley, of course, moved. He became Astronomer Royal in 1721. So in general, it's a period where we see an introduction of particularly mathematical techniques and other methods into areas of practical and state interest, like surveying, gunnery, navigation, and so on. So it's that kind of support, both among groups of like-minded individuals and from those who actually hold the purse strings, that allowed the young Halley to be supported to undertake voyages that related to scientific and astronomical observation. So he was supported by the Royal Society and others to make observations of the southern stars, southern hemisphere stars, by making a voyage to St. Helena in the Atlantic, where he also had the opportunity to observe a transit of Mercury. And also later on, at the point where he got made a captain in the Royal Navy, he was carrying out magnetic observations and other kind of surveys around Britain and in the Atlantic. It's the case that no transit of Venus took place in his lifetime, but it's apt because of these experiences that he had of being himself an expeditionary observer, that he is the one who had a vision of observing transits of Venus in the future, relating them to sea voyages and the kinds of access that European empires were giving to people like him and other astronomers to other parts of the world where they could make different kinds of observations. So in 1716, Halley followed Kepler, who himself, as I say, had died before he had a chance to see a transit of Venus, but had made a warning, he had made an admonition to other astronomers to look out for this thing coming in the future. And Halley followed that example for the next two transits of Venus that were predicted to be coming up. So 1716, he published his warning to astronomers, as he said, to young astronomers who may perhaps live to observe these things, looking all the way to 1761 and 1769. So he was flagging those future events, as he said in this quote that I've taken, I recommend it, therefore, again and again to those curious astronomers who, when I am dead, will have an opportunity of observing these things, that they would remember this, my admonition, and diligently apply themselves with all their might to the making of this observation. So he made that comment, made this point, talked about a method for observing transits of Venus at the Royal Society. And it was also then published in Latin so that it could reach a wider European circulation and warn astronomers beyond Britain as well. So he published and circulated that method for observing the parallax of the sun, which is why observing the transit of Venus is interesting, and from that making calculations of the distance between the Earth and the sun. There's a part of the diagram there from a 1761 publication by James Ferguson, which contained a translation of Halley's text. So that's where this English version of it comes from. So Ferguson, of course, pointing out that it's coming right now by the time he's publishing that. Halley had circulated and made his warning. And his method involved observing from different parts of the Earth, ideally, and that's what this diagram is partly showing, that would give different timings for the passage of Venus across the sun, from which the parallax could be calculated. So he worked out that there were different parts of the world in which the whole of the transit, so right from the ingress to the egress of the planet across the sun, and would be visible. And if you observe them, he suggested, at very different latitudes, you would get different timings. So Venus would appear to be moving on different parts of the solar disk, and it would be, he suggested, he didn't know the distance, so he was estimating here, that it would be at least 15 minutes longer observing the transit if you were in somewhere very far north, and he mentioned Port Nelson and Hudson's Bay in North America, somewhere where the British had an occupation and access to. It would take considerably longer there than it would if observed in the East Indies. And again, he talked about British possessions there that would be well placed. He mentions Madras and Bencoolen on Sumatra. So his point there, of course, is that the British as astronomers and as a naval and increasingly imperial nation, were well placed to do this work because of the access that they had. So the onus was on them in the future, he suggested, to do it. He also pointed out that the French might be able to take advantage of their possessions, for example, saying that there could be a skillful observer placed at Pondicherry in the Bay of Bengal. And the Dutch, he said, could use Batavia if, he said, they had the disposition to assist. He seemed to be casting doubt on whether the Dutch would do that. The more, he said, the better in terms of observers, because of problems that might come up, including cloud cover, which would stop you making these observations. So why was this something that Halley felt people ought to do, or that anyone else joined him ultimately in deciding that this is what they ought to do? Now I'm going to go through some text here, and I hope that I'll be more or less synchronized between my bullet points and what I'm saying, but if not, you'll be able to catch up, hopefully. So nice to know, yes, that's something I think people feel now. We just like to know our place in the universe. We would like to know how far away the sun is, or Venus is from the Earth. But of course, something just being nice to know doesn't necessarily get you the kind of funding that you need to carry out a voyage and these kinds of observations. Certainly, there's also the idea of glory attached to knowing. Glory for sort of humankind generally, but also glory for those who do it personally and for those who choose to fund it. So monarchs perhaps are sort of tickled by the idea of being able to claim this kind of knowledge, particularly something that seems so sort of heavenly and sublime, and also demonstrates their national prowess, the powers of their astronomers and their navies of getting them to places where they make the observations. For Halley, this is important too, but he notes that essentially he's putting forward the idea that one of the benefits of doing this is showing the power of mathematics and of observing as well, to be able to work out this problem that seems inaccessible to us on Earth, but actually mathematics and observation can allow us to do that. And showing the success of this, and that you can get results, of course, is important for persuading patrons to support mathematicians and astronomers and others, even if it's something that seems not immediately practically useful, what we now call blue skies research. But there are payoffs as well. So as we perhaps have already heard, the idea of international competition to getting to this knowledge, or being seen to be part of it, is certainly an important driver. Although ultimately, as I'm sure you know already, the ultimate project was very much one of collaboration, lots and lots of observations, lots of observers, lots of different nations involved. But the desire to lead on this, or the desire not to be left out, clearly was also an important driver. And adding to this, in the 18th century, of course, is imperial competition, particularly amongst those more ambitious nations. And France and Britain are very often at war in this period, particularly in areas around North America and the Pacific, just those areas where they would be going on for observing expeditions like this. So showing that you have influence, imperial control, that you can get to these places, that you can stake a claim to them, that you are acting in effective and in scientific ways in these parts of the world, was also crucially important as part of asking for money and receiving it. And of course, after the 1769 transit of Venus observations, as we've already heard, a link to James Cook, there was an astronomical observation and project going on, but also a subsequent project to try and locate new land and find the potential usefulness of the natural resources of a supposed southern continent, and to claim it for the king. So a sense of that was already evident in Halley. He didn't know, of course, that when it was happening in 1761, this would be very much against the background of the 7 Years' War, which increased this competition and made access to the places of trying to go sometimes very fraught, shall we say. Beyond this, also, there is the desire to prove astronomical tables, and that's there from the very beginning and continues to be the case. Testing predictions, but also the promise of improving the accuracy of positional astronomy and its tables is in there. So you're plugging much better, sort of real, potentially quite good, and not just relative ideas of distance and masses of the sun and planets into your calculations. From this, there is also then the link to the improvement of navigation. Improvement of astronomical tables can always be sold, and always was sold to kings and others as being an improvement to navigation and to surveying, relying on astronomy, making more reliable charts, allowing more exploration, improving maritime trade, creating new trade routes, more commerce, more reliability, etc., etc. It was always sold this way, and links any improvement to astronomy is presented as being ultimately good for the nation in those ways. So what was required to make all of this happening? In his text, Halley glossed it as being with some warning and preparation. He suggested something that's doable, he said, without a great deal of labour. He did try to come up with a relatively simple method, and one that perhaps could be done by people who were already in the locations he specified. But it was hardly the case, really, that it involved not a lot of labour. So we'll think about that, and then think about its impact. So I'm moving on to a slide that shows a map of the areas in which the 1761 transit was observable, either in whole or part, and that's by Joseph-Nicolas Delisle. And here's someone who took the call of Halley particularly seriously. In fact, Delisle visited Greenwich and had spoken to Halley back in 1724, so they may have discussed Transit Venus then, and of course Delisle lived long enough to see it, whereas Halley didn't. He was the official astronome de la marine by this period, which he wasn't then, but he was put in that position subsequently, and he drew up this map for presentation to the king, French king, in 1760 in advance, and circulated 200 copies to other astronomers and academies. So taking up again this idea of the warning, this is where it can be seen, this is where you need to position yourself to do it. Britain had not forgotten that this was happening. There were some letters and articles, for example, in the Gentleman's Magazine about the idea of sending out observers, but there doesn't seem to have been a great deal of official interest in what was going on. And it seems that the Royal Society was almost surprised to find out that the French had developed plans to a considerable degree by 1760, and suddenly felt that they perhaps ought to try and catch up themselves as well and not be left behind in an effort relating to this event. The method that Delisle was proposing was a little bit different to Halley's. It was focused on timing the moment either of ingress or egress from different locations, rather than timing the whole of the transit itself. So getting the moment of ingress, egress captured, and that relied on greater accuracy of clocks and greater accuracy of knowledge of precise locations, longitude and latitude from where the observing was being made, which Halley thought was perhaps a bit too difficult. So this relied very much on precision observation and instruments, which were perhaps more accessible by the 1760s, but also required plenty of effort and organisation. And ultimately, plenty of people did. There were something like 176 observers, 10 countries, 120 locations, and many publications that came out of this. But what was needed for the process? This slide shows some instruments of the sort that would be required. And the quote that I have up there is the immediate response, essentially, at the Royal Society after hearing about the French plans. Of what they would need if they were going to very quickly bring together some expeditions themselves. This is James Bradley, then Astronomer Royal, recorded in the Council Minutes of the Royal Society, suggesting that you'd need a 2-foot reflecting telescope with Dollond's micrometer. So you can see an example there from the National Maritime Museum collections, the sort of portable heliometer for measuring small differences between the solar disk or measuring positions across the disk in an accurate way. Also a refracting telescope of 10 feet, a quadrant of the radius of 8 inches, he suggested, and a clock or timepiece, and that would have to be a fairly good one. This, in a sense, is the minimum kit for an astronomical expedition, and it's what, in essence, defines the kind of precision of precision exploration that I'm talking about. The quadrant and the clock were for making the positional measurements rather than for observing the transit itself. So that business of establishing exact longitude and latitude and exact local time from the observing position, something that would take at least several days to do, and the longer you had to do it, the better and more accurate it would be. So it became quite a process and not just the observation on a single day. You also need money to do these things, acquire these instruments. And the 1761 expeditions were successful in getting support from George III, offering £100 to each of 2 expeditions organised by the Royal Society, also the support of merchant and Royal Navies to the extent that they use those ships. And those are the 2 expeditions that were sent out, one to St. Helena, one that was meant to go to Sumatra, one of the sites, of course, that Halley had pointed out, although in the end, because of the 7 Years' War, they were foiled and only got as far as Cape Town, although they were able to make Mason and Dixon of Mason and Dixon line fame, which they went on to do, did manage to make an observation there, whereas Maskelyne and Waddington and St. Helena were foiled by clouds. So Maskelyne, one of the observers for 1761, found this occasion was one that, in a sense, defines his whole career, despite being foiled by clouds. But it gave him lots of experience of observing on ships and on expedition in the field. He went to St. Helena, which is where Halley had observed the southern stars nearly a century earlier. And he wasn't, in the end, too worried. I'm sure he was disappointed on the day by the transit of Venus failure, because he had created an observing plan that wasn't just reliant on that, but made the most of his opportunity of being in a different location. So he was also observing stellar parallax of Sirius, not particularly effectively, but made a series of observations that gave him plenty of experience and set in train his program of work to try and measure the effects of gravitation on a plumb bob, so the attraction of mountains, trying to establish the gravitational pull of large masses of rock. He was also investigating the effects of gravity on the going of a clock, so on its pendulum, and had set out to compare the effect of that at St. Helena compared to Greenwich as part of investigations around this period and before and after of establishing the shape of the figure of the Earth, as whether it was an oblate spheroid or not. He was also making observations of lunar parallax, which was also about comparing observations at other latitudes. He was interested in magnetic and tidal observations, and he was also trialling the lunar distance method of finding longitude at sea. So he did that both on the voyage over and on the way back. And that was something that led to much of his subsequent work, both immediately on his return and, of course, also after he became Astronomer Royal, which he did in 1765. And very quickly set up the publication that made the lunar distance method one that was practical to use at sea, which was the Nautical Almanac. So this experience in general set him up very well to be the driving force organising the 1769 effort for the transit of Venus, observing from Britain, and of course working to expand the role of astronomers beyond transit of Venus expeditions and driving the kinds of astronomical observing programs he was interested in, bedding in the Royal Observatory as a place where those things could be managed from. So in general, slight disappointment in 1761 and a determination to do something rather more impressive in 1769 from Britain, from the King, from the Navy. The war, 7 Years' War, had also ended, which allowed more focus on this, more funding, more observing sites, support from the Admiralty as well as the Royal Society, and it became tied to this exploration effort on top of the observation of the transit of Venus itself. And you can see some quite large sums of money being expended in supporting particularly the chief expedition of Cook on the Endeavour, but also 4 other observing sites used as well. The location that Cook went to on Tahiti was one that was essentially rediscovered and confirmed as being a very well-placed site with the return of a recent circumnavigation of the Dolphin, which was commanded by Samuel Wallis and had circumnavigated in 1766 to 68, so came back to Britain just in time to note the position of Tahiti having been re-established. And also is a note that reminds us of Britain's increasing interest in maritime exploration to consolidate and expand trade in this period after the 7 Years' War. Not going out with observers of men of science on that occasion, but certainly this desire to continue to find more of the world. So yes, Cook and Endeavour being sent to Tahiti before then going on to explore further in the southern seas. On Tahiti, they set up Fort Venus. You can see the huts there, which protect the expedition, all its equipment, and also the observing instruments. But also, it certainly was a fort. It is fortified to the extent that there are walls and bars around it, but also they have a military presence as well. There were guns, there were Royal Marines there to support them. The equipment was carried on the ship, of course, and sheltered on Tahiti in those observing huts and tents. Actually, not tents at this occasion, huts. And again, we have this sort of key suite of instruments, and these images are objects from the National Maritime Museum, also the Science Museum and the Royal Society. There were, at the time, several examples of these because same or similar instruments were being sent out with each of the expeditions to try and make them more comparable. And they were made by some of the best instrument makers of the period. The quadrant by John Bird, the regulator clock by John Shelton, who was the apprentice to George Graham, who'd been one of the, perhaps the most respected clock and instrument maker at the time. And these names generate trust in the instruments to the extent that you can trust them at all. So also John Dolland, Jesse Ramsden and James Short associated with the telescopes that went on these expeditions too. The actual clock, that's the one that belongs to the Royal Society now. I forget which expedition it went on. The one that actually went with Cook is probably the one that's now at National Museum Scotland, where I am now. So I should have put a picture of that in, but apologies. This one looks nice because it's set up with the sort of tripod that was used to make it portable then. So you have the money, you have the location, you have the instruments, but as well as those things, you certainly need the skills of the observers. Sorry for this image representing Charles Green. There's no portrait of him. He was the lead astronomer, however, and this is from a school sort of kit for a game, I think from Australia, that introduces many of the individuals associated with Cook's voyages. He was himself a former teacher of mathematics, but also went on to become an assistant at the Royal Observatory in Greenwich, working under James Bradley. Before becoming an expeditionary astronomer in various ways, he was an assistant to Maskelyne on another voyage that he did after his St. Helena one for a trial for the Board of Longitude of 3 different methods of finding longitude. Went to Barbados in 1763 to 4. Green stuck with the Endeavour expedition after Tahiti. It wasn't that he just went out to do that. He stayed with the expedition on to New Zealand and Australia, where he made observations on land to fix positions as accurately as possible. And of course was making use of things like the new nautical almanac and still relatively new observing instruments like the sextant to further test the lunar distance method at greater distance, and also interested in teaching others on that voyage to use it as well, so that it was not just something in his hands but something that the other officers might be able to do as well. He was supplied by the Royal Society and also by the Board of Longitude with a whole range of instruments to carry out survey observations of geomagnetism, meteorology, hydrography rather, and so on, though sadly he died in 1771 at Batavia. Cook was there because he's not only the commander of the expedition, but he was also officially Green's assistant as an observer. This portrait shows him in 1775 after his second voyage, or sixth, I've written that, sorry. And his reputation by then, as that portrait perhaps makes clear, was secured. He was captain at that point, he was lieutenant on the first voyage. He got made a captain. And while Green's story tells us about the sort of gaining of mathematical and observation skills in a place like London, where you might teach, where there is work at places like the Royal Observatory, and in its production of the Nautical Almanac that he did calculations for. And that's a story that sits behind many of the transit of Venus observers that I'll point to some more of them later. Cook's story tells us about the gaining of these skills in a maritime and overseas sort of context. He had begun as master of a naval ship, and he gained his navigational and surveying experience at sea and overseas to North American waters and during the 7 Years' War. So he tells us that it could be an advantage, a way of gaining recognition in the Navy, and that became ever more so the case with his own success for others following him. He had got a practical, essentially, training in mathematics and astronomy while at sea, and also had gained a introduction to the Royal Society when he observed a solar eclipse while in North America in 1766, and he sent an account back to the Royal Society, which was read and explains why they, as well as the Navy, sort of had learned to understand that he was capable of making the range of observations that would be required, including lunar distances. So he was undertaking that method as well as running surveys and undertaking charting overseas. So the Endeavour voyage was indeed a success, and a year after his return, Cook was being sent out overseas again. That was something that now didn't have an astronomical objective attached to it, something like the transit of Venus. That was been and done and was not coming back until the later 19th century. So Cook was skilled as a navigator and a surveyor. Other officers might be as well. But there was civilian artists and naturalists being sent with this because of the success of finding species, plants, animals overseas, the art that had been brought back and was exciting to people when they saw it. Those things were going to be replicated. But actually there was no specialist astronomical expertise now that the transit was over on that voyage, that second voyage, as it was initially planned. But Maskelyne himself took the opportunity and decided to intervene. So he wrote to the First Lord of the Admiralty, who was therefore also a Commissioner of Longitude, Lord Sandwich, who had been something of a patron to him in 1771, saying that the voyage that was planned, he thought, could be rendered more serviceable to the improvement of geography and navigation than it can otherwise be if the ship is furnished with astronomical instruments, as this board, that is the Board of Longitude, hath the disposal of, or can obtain the use of from the Royal Society, and also some of the longitude watches, and above all, if a proper person could be sent out to make use of those instruments and teach the officers on board the ship the method of finding the longitude. So it was an opportunity he could see to do a number of things. One was that stress on teaching, so to continue to try and increase the number of officers within the Navy who could use the lunar distance method, make use of the Nautical Almanac, but also to make use of timekeepers. In this case, the longitude watches he refers to are the ones made by Larkham Kendall, based on John Harrison's Sea Watch, and also by John Arnold. It's not the case that Maskelyne was uninterested in promoting the timekeeping solution to longitude, although that has been suggested in some texts. It was also an opportunity, as Maskelyne knew, to make accurate determinations of longitude on land. So if you had this proper person who was skillful with good instruments, they could go on land, make good observations that would test, see how well the navigation methods were working. It would also provide future fixed points for navigators to work from in the future, and of course would be something that you can base accurate surveys and charts on. It was also a way of making use of the kinds of instruments that the Royal Society had gathered as a result of the Transit of Venus expeditions, and also the Board of Longitude, things like the timekeepers, also its involvement with the Transit of Venus. So these instruments had been acquired from that effort and they were still available. Things could be done with them. So the Board of Longitude agreed that Maskelyne should head a committee to find 2 observers, not just 1, but 2. And they said to prepare a draft of instructions proper for the said persons and also a list of the necessary instruments. Maskelyne selected 2, William Bailey and William Wales. Both of them had previously observed transits of Venus. William Bailey, he knew as an assistant at the observatory, and William Wales had been a computer for the Nautical Almanac. Sorry. So in terms of instruments, instructions and personnel, all of this being overseen by Maskelyne, the voyage really followed the model of the previous ones. In terms of this decision to insert astronomers, specialist observers, and the expectations of precision rather than a more general kind of survey and observation onto a naval voyage of exploration that now lacked that primary astronomical purpose or initiative from the Royal Society that had got the Transit of Venus expeditions working, I would suggest it sets the pattern for the future. And we can see that it really does become a pattern in terms of how Maskelyne set up lists of instruments and instructions in text for observers to use in the future. So this is from a list of instruments from the minutes of the Board of Longitude that shows instruments to be loaned by the Board of Longitude or borrowed from the Royal Society or purchased in addition to support Cook's second voyage and the astronomers going out on it. And this, in a sense, becomes a sort of defining list of instruments of precision exploration and becomes the model for subsequent voyages. A few more get added on beyond this, and also something that never gets left off again includes various texts, particularly including the Nautical Almanac. 12 copies, he said, of the Nautical Almanac for 1772, 3, 4, and as much as can be printed for 1775, hot off the press, were all to go off as well. So we get very similar lists for other voyages of exploration that take place in this period. For example, this is a list of the instruments going on Cook's third voyage. There's a very similar list as well that goes to Constantine Phipps's voyage to the North Pole for 1773, just before this. Also for the Sirius flagship of the First Fleet in 1787, and to George Vancouver's voyage to the Northwest Pacific in 1791. So all of these become scientific and precision expeditions. Sorry, talking too long. Note the web address that I've given here. All of these can be seen sorry, at Cambridge Digital Library, which has the Transit of Venus, the Board of Longitude archive and additional material from the National Maritime Museum. So, a fixture from the second voyage of Cook onwards was the portable observing tent, which was designed by William Bailey from his experiences on that. And that again becomes something that is always put on these lists. The observing tent is a key part. It notes that to make a precision observation, you need to set up on land for a period. Your instruments, something delicate like these regulators, need to have protection, and you need to try and take as many observations as you can while off the ship for precision. Ships are good, of course, though, because they're large enough to carry a fair amount of equipment. It's not like you're doing this on horseback or by foot, but you can take a fair amount of equipment, and there will be occasions to stop and set up on land and make those precise fixes by astronomical methods. All these board of longitude observers that were sent on these expeditions, so not only are those lists of instruments, but also each of those are attached to an observer being sent out as well. And they continue to be encouraged to try and teach members of the ship's crew to use the new and more precise instruments and techniques that were going out with them. They were navigating by timekeepers and by lunars. And surveying effectively, increasingly without the layperson alongside them. They were gaining these skills themselves, and increasingly the Navy itself could supply the kinds of instruments that initially we only see coming from the Royal Society and the Board of Longitude. These are a list of the observers on these British voyages of exploration, and the one
Oh, I think we've just lost Rebekah, so we'll just give her a few seconds to see if she can rejoin us. Has everybody, anybody else lost Rebekah as well, or is it just me?
No.
She's gone.
Yes.
Oh, okay. It does appear to be a little warning triangle in her thumbnail.
That's what that means. That's weird, isn't it? Low bandwidth.
It says that low bandwidth.
Yeah.
Yeah, it's okay.
I wonder if she's aware.
Unfortunately, let me see if I can contact her.
Can you hear me?
Oh, we can now. We
I'm
lost.
very sorry.
It's okay.
My computer ran out of battery.
Ah.
Didn't give me a warning, it just went. But I'm back now. Sorry, and also very nearly finished. So I will just get through to the end.
No
where
worries.
I got to. So yes, these are the expeditionary astronomers on these voyages of exploration, scientific exploration. The ones marked in red are ones that Maskelyne knew and often had worked with as people who had worked as assistants at the Royal Observatory or as computers for the Nautical Almanac. So you can see that this is an opportunity. Some of these people come back again and again. They're making careers as observers and computers in a sort of a slightly ad hoc manner, but having a patron like Maskelyne obviously allows them to develop their careers that way. The ones in green were naval or military officers, but not so many of them yet at this period. Others were mathematically trained, experienced in other ways, and often became known to Maskelyne through the need for these observers. And we can trace lineage in some cases, people who were taught initially by people like Green and Wales in the early voyages, as well as Cook himself, who then become effective observers themselves and navigators. So people like George Vancouver and William Bligh, later known as good navigators and surveyors, having been trained by Cook, but also by people like Green. Some of these men also, Wales, Bailey, Inman, went on to become teachers and professors at naval colleges and schools. So we get these skills being sort of honed at sea and through these connections, but then being brought to the classroom to teach future naval officers. After this, we had a hiatus essentially with the French wars and no expeditions going out. But the Board of Longitude again became involved with sponsoring and supplying observers with a sort of a new burst of interest in exploration of the Arctic from 1818. And we see something of this beginning again. When the Board of Longitude dissolved in 1828, its functions by that period essentially could be brought on internally into the Navy, including the kind of technical expertise that these people had can be found in places like the Hydrographic Office of the Admiralty of the Navy and within the naval colleges where the teaching was taking place. So from the 1830s, we get precision survey voyages, ships like the Chanticleer and the Beagle, which were clearly a continuation in their techniques from these earlier voyages, but happening without necessarily needing to bring on this kind of external expertise that was required in the 18th century. These rather lovely images are from made by a Royal Navy officer, Owen Stanley, who trained at the Royal Naval College in the 1820s. And in the 1830s and 40s, he went out as a first midshipman, HMS Adventure, and then as a commander of HMS Rattlesnake. So we can see all the precision instruments and the tents, that key marker, being set up in these drawings, but they're all being manned by naval officers rather than by astronomers. Or at least they may be astronomers, but they're not lay persons, they're people making their careers in the Navy. So this precision approach to survey would have developed, I'm sure, within the Navy by the 19th century, by whatever way it was, but it's striking that the effort surrounding the transit of Venus in the 1760s gave maritime experience to a series of astronomers and experience of transporting and using precision equipment to a series of naval officers and men at just the right moment. Maskelyne takes his opportunity and makes sure that a continuous tradition is started up, makes use of the instruments, makes use of the skills of his observers at sea as a deliberate push by Maskelyne and by the Board of Longitude more generally to get the new techniques in use at sea and being taught by experienced men to training officers. So in essence, that is probably more significant than the actual transit of Venus observations themselves, which had somewhat mixed results. So I'll finish there. I've got a little bit of further reading, particularly pointing you to those online resources, the papers of the Board of Longitude at Cambridge Digital Library, which are well worth having through. Thank you very much.
Okay. Right. Well, I'd like to say, first of all, on behalf of everybody here, thank you very much for the talk this evening, Rebekah. I must congratulate you on the way you're battling through with the problems with the voice, but appreciate it in the end. I, for one, find this very fascinating, the way that things were done back in those days, particularly hearing about the reasons why these expeditions were put forth, because the modern day equivalent of what we have today with all the missions to Mars like Perseverance and whatever, the rationale is still the same, although I think the funding is somewhat slightly different. I was interested in how they itemised the shillings and pence. But yes, I think that was marvellous, and it was interesting to hear how things were done back those days and how we developed them today. So if I can ask everyone to unmute themselves, please, and show our appreciation. Right, thank you.
Apologies for the coughing and for then losing my battery. And I think that's the first time happens doing a talk. I've suddenly disappeared. Right. Thank you for sticking with me.
Well, if it's, I'll just check if it's okay with you, because we do have some questions that people have been putting in our chat whilst you were giving your talk. Would you be able to hang on a bit longer and hopefully go through some of these questions for us?
My picture's gone as well, hasn't it? I've just seen.
Yeah.
Yes. Apologies for that. I think I'd have to log off and shut my computer down again. Otherwise, my camera doesn't like it when it closes down suddenly. So if you don't mind a disembodied voice, I'm very happy to answer some questions.
That's fine with us, as long as you're okay both with your voice and your time, if you can continue for a while with us.
That's fine, yeah.
Okay, thank you. Right, one of the first questions that came up at the beginning of the chat, and I think you have been talking about some of the aspects of it since the question was put on there, but basically the question was, how good was the timekeeping back then?
I don't have a very good answer to that, I'm afraid, or at least not offhand. Yeah, I could perhaps throw it open to other people who might have a more ready answer than I do to that.
Right. Okay, I think because this was obviously well before the development, was it the Harrison timepieces where?
No. So this is absolutely at that time.
Oh,
Harrison's timekeepers were being trialled by Maskelyne and others in the 1760s, and they were the model, as say, for one of those timekeepers that he sent with the second voyage of Cook, made by Larkham Kendall. So yes, if we're thinking about sea travel and timekeepers on board ships, we have this period timekeepers that can keep time sufficiently well to keep your longitude within a degree. That was the aim of the larger prize that the Board of Longitude was offering. Accurate to about a second a day, suggests Lee. I don't know, to be honest. It's not a question that particularly interests me, but it's always the one that I get asked when I give talks to Astronomy Society, so I really should write it down. They at the time thought that the lunar distance method potentially was more accurate, as providing you were well positioned and you could take a series of observations in order to make it as accurate as possible.
okay, fine. Again, earlier on in your talk, you mentioned a number of times the lunar distance method, and one of the questions is, what is actually the lunar distance method?
So that's making observations of the distance between the moon and another star in the sky. So these were things that could be predicted and were those positions were the things that went in, among other information, into the Nautical Almanac. So it would tell you what time a particular relationship between the moon and another star, what were known as the clock stars, sort of along the line of the ecliptic, were the key bright reference stars that were used. And the Nautical Almanac would tell you what time that should appear if you were at Greenwich. And then making an observation at sea of the same thing, you would work out what your local time was somewhere else as you made that observation, and then take one away from the other, essentially to give you your longitude, so how far east or west of Greenwich you were.
So how long was that in use before it was superseded by subsequent technology?
Yeah, that's an interesting question. They were, I always like to stress when I talk about the story of longitude that in the later 18th century and early 19th century, there were very much complementary methods. It wasn't either or. And indeed, you're also doing basic techniques like dead reckoning, keeping an eye out, all the things you want to do when you're at sea. And on expeditions like this, where they had the skills and they had the instruments, they were absolutely using both things at the same time, particularly when you had to make critical decisions about your navigation, whether, is it the moment to turn or are you going to hit something? And that continues to be the case in the early 19th century. By sort of the 1820s, there are enough timekeepers around that you could probably travel with 2 or 3 or more of them, and that allows one to be a check on the other, and it's an easier method to use the timekeepers than to make lunar distance observations. But they were still used, or astronomy was certainly used to check the going of the clocks, or make your observation of local time and so on. So the astronomy and timekeepers absolutely go hand in hand in this period. Astronomical techniques developed over the 19th century and continue to be used. It continued to be part of training until the 20th century. It's sort of gone out. We now have position finding of various sorts, but actually have more recently been reintroduced because of the concerns about security of things like GPS, which could be blocked, or the signal could be interfered with. And in the end, if all your systems fail, you still need astronomy. It's your basic way of finding. If you're absolutely lost, it's the only way to recover your position.
Well, actually, that follow-up question to that was, how does the accuracy of those original instruments compare to today's techniques and instruments? And has anyone ever used those historic instruments today to try and replicate the measurements that they made?
Yes, I believe people have, but it's, again, not something I'm afraid I know a great deal about. It's certainly nowhere near as accurate. I mean, a quartz watch or something is going to be far, far more accurate than any of these observations. You tended to, work well ahead of yourself when you're making observations for navigation. Assume that you're closer to something than you are, so that you don't accidentally come across it unexpectedly. So there is a great margin of error, not surprisingly, given the techniques, and given that you're making observations while in motion on, a wooden ship at sea. So I think in essence, not comparable, but Lee or Louise may have a more precise answer for you than I can give you.
Okay, thanks very much. Another question, again, regarding the instruments. You showed us illustrations and photographs of the different types they took with them, but did they actually have any backup instruments on these expeditions? Or were there members of the staff or crew there who could actually effect repairs if necessary? Because it seems an awfully sort of time to go to have something done at the last minute.
Yeah, that's a really interesting question, and reminds us of the kind of skills you need to maintain instruments, or what do you do if you break it or lose it, and so on. And there are some great stories about that in the period. They had a number of things like telescopes. So, Cook had his own one that he lent to the expedition. So they had backups in that sense. They would have had a number of things like sextants or octants available. Things like the astronomical quadrant, the sort of brass instrument that was on a stand, was an expensive and more unavailable kind of piece to most people. So there would only have been one of those on the expedition. And if that had got broken or lost, it would have been a big problem. And there were issues with native people in Tahiti stealing, stealing from the point of view of the people on the Endeavour, sharing, borrowing from the point of view of people in Tahiti who have a very different idea about the nature of property. But there was an issue with a sextant being stolen, and reprisals. I think that the person who stole it had their ear cut off. So there are misunderstandings, shall we say, unpleasant incidents like that. But that tells you how important the sextant was seen to be, and how they risked a lot to get it back. Repair would have been a big issue. You wouldn't necessarily have had the skills to do that. We have examples on some of the expeditions of finding someone at a place overseas that's not going to be readily available in Australia, but somewhere like Rio, for example. They came across someone who had experience as an instrument maker, who was able to repair a chronometer that was broken. So those things increased over time, shall we say. But yes, they were fragile and difficult things to use in the early days.
Okay, fine. I've just noticed we had a comment on the chat from Lee. Quick, about a second. I assume that might be in relation to the question we had earlier about how does the accuracy of the original instruments compare to today. Is that correct, Lee? Or?
Yes, it is. Yeah, I think that's roughly the accuracy one expected of a pendulum clock. Can you hear me? Sorry.
Yes.
Good. Yeah. It's the but on the other hand, Harrison's H5 chronometer was tested to have lost 4.5 seconds in 10 weeks, which was incredibly accurate for 1772. And that's the kind of accuracy you needed to get a really accurate fix of your longitude at sea after a long period away from port.
All right, great. Thanks very much for that, Lee. Okay. Now, speaking of which, again, another question. We mentioned earlier the longitude watches. a member's asking, how actually did the longitude watches work?
I'm not a horologist, so I can't tell you how they actually work. Obviously, the method is to, rather than finding your local, using astronomy to find out what the time was at Greenwich to compare with your local time, you're keeping time, you're taking it with you. So you're keeping a constant track of it rather than rediscovering the time. So again, it's a basic, taking the point that longitude is the same as a time difference between two places as you move around the world. The timekeepers that worked well were ones that didn't use pendulums, like those very accurate astronomical regulators, because you can't use a pendulum on a ship while it's moving around. So it ended up being something much more like watchwork that underpinned the development of chronometers. It's not, Harrison is not in fact the person, although he's the person who showed it could be done, and his H4 trialed successfully and showed the accuracy that could be achieved. It wasn't actually his particular innovations that were the ones that ended up being what we think of as a chronometer by the end of the 18th century into the 19th century. So it took the work of Frenchmen, Pierre Leroy, Ferdinand Berthoud, and also John Arnold, I mentioned, and Thomas Earnshaw working in London to develop the range of technical elements of these timekeepers that made them light, accurate, and portable, and maintaining their time over a long period. But yes, you would need to ask a horologist for the full details.
Okay, thanks very much. Last one I've got here. I'm not sure if this is pertaining to all the equipment or particularly to the astronomical equipment which we had the interest in, but presumably the instruments were temperature sensitive. So were you aware of any attempts that were made to keep them at a constant temperature, particularly in these far-flung observing locations?
Yeah, I mean, obviously, so the temperature compensation is one of the key elements that Harrison solved with his several timekeepers, not just the Sea Watch. So using bimetallic strips, he used different metals to compensate for expansion and contraction, both in his regulator clocks and in his marine timekeepers. So that was an innovation that is taken up and was very important for this. Less important for the other kinds of instruments, perhaps the clocks, once they're set up, can be made to keep good time within the environment that you're in when you're set up on land. Obviously, having the tents probably helps maintain a more constant temperature than you might have if you're sort of more exposed. Again, with the kinds of levels of accuracy that we're talking about in the instrumentation at this period, it's probably makes less of a difference than it might once you've got a more accurate possible reading. So you don't hear it being talked about very much apart from with the timekeepers at this period.
All right, thanks very much. Okay, well, I think that's it for now for questions. So just once more again, I'd like to thank you very much for your talk this evening. And again, ask once more everybody if you can show appreciation to Rebekah.
Very much.
Okay, well, Rebekah, we're going to continue with a bit of in-house talk and chat with you. You're quite welcome to remain if you wish, and anybody else can do so. But again, thank you very much.
Thank you. I think I might go and give my computer a rest and my voice as well. So apologies for those interruptions, but thanks very much for your questions.